Hello, this is Jeffrey Curtis, and the title of my talk today is How many particles do we need to measure the aerosol mixing state? This is primarily the work of Jessica Gasparik and in collaboration with some folks at CMU. So, in terms of thinking about aerosol populations and aerosol particles, as we know, aerosol particles are very complex in terms of composition. And then additionally, aerosol population is a collection of really complex particles. So that makes it very complex. So the way we like to think about it in terms of how it evolves over time is this schematic here, where on the left we have some background aerosol that all looks very homogeneous. Is this aerosol is infected over an urban area, it experiences emissions of particles that are very different, and this is going to actually make the particles look less homogeneous. Particles over the urban area are going to start to age due to coagulation and condensation, which makes the particles look more similar. The particles eventually are transported downwind of the urban area, and they'll continue to age, and um, it may or may not go over another area of emission, either maybe over the ocean here as we have in the schematic, or over the urban area. Once again, injecting emissions of particles that look very different, and so on. So as we can see here, if you think of how the aerosol mixing state is evolving, it's very complex. It's becoming more homogeneous and less homogeneous over time. So why is knowing the aerosol mixing state of such great importance? So here I have two examples of how aerosol mixing state can be very important. On the left here, we have the same amount of bulk of ammonium sulfate and hydrophobic organics, but we've distributed them differently amongst the six particles here. So in this case, we have an external mixture where we have three particles of each that are one pure component. We have the internal mixture in the center there. These particles all look exactly the same. And then on the far right, we have what we consider the real world mixture. The implications of this distribution may result in different number of particles being activated as CCN. This is from Reamer et al. 2019. Then on the right, from Kodros 2018, in terms of thinking about optical properties, what we have here is we have the same amount of BC mass, the same amount of aerosol mass, and the same number of particles, but we can distribute the black carbon differently amongst the different cases. So not to get into the details of this, but as we can see here, there's many different ways to think about how the black carbon may be distributed amongst those particles. It's going to have an impact of the number of particles that contain black carbon, so it's the number of particles that absorb. It's also going to change how different particles absorb. So it changes the absorption of the entire particle population. In terms of thinking about how to think about mixing state, we have a quote here from Winkler 1973. The same net composition of an aerosol can be caused by an infinite variety of different internal distributions of the various compounds. So what Reamer and West 2013 have developed is a mathematical framework based on diversity metrics to look at these different particle populations and tell us how internally or externally mixed these populations are. So here on the left here we have an external mixture where each particle is one single component. And on the far right we have an internal mixture where all particles look exactly the same. So this chi value, which is the mixing state, is 0 when particles are fully externally mixed and 100% when fully internally mixed. And the nice thing about this framework is it allows us to determine where intermediate populations exist between internally mixed and fully internally mixed. However, this requires per particle composition and mass fractions. So in terms of mixing state, to go back to like sort of my first slide where it was sort of a simple cartoon of how mixing state evolves, here I have some field measurements from two field campaigns. On the left we have some work by Rob Healy at Megapoly, and what they did is they measured the measured per particle mass fractions um, at a single site. And at the top here, we can see how the mixing state value chi varies over the period of time that they were measuring. Additionally, we can also see how mixing state varies horizontal in the spatial scale, where we have from Yi 2018, which is also one of the collaborators in this project here, is they measured the aerosol mixing state is a function of space in the Pittsburgh metro area. And as we can see here, upwind of the urban area, they had more internally mixed particles, and then in the urban area where we have the emissions, the mixing state varies quite a lot, and then particles obviously move downwind. So this gives us the idea that mixing state is very important. It's also varying spatial and temporally, so creates quite a challenge. So what I want to do here is give you the idea of how difficult it is to get an idea of what mixing state looks like. So what I'm going to do here is I'm going to reveal a series of particles, and basically we can measure the bulk, but we don't really know what the mixing state of the entire particle population is with very few particles. So the idea here is the premise of this project is here we have 250 particles. How many of these particles do we actually need to sample with measurements to have a confident idea of what the aerosol mixing state actually is? And we'll get to the answer, how we investigated that problem and how we answered that problem. So it's very difficult for measurement people to conduct a huge sample size of particles that we would need for this project. So what we did is we did this numerically using the model PartMC, which is a particle resolved aerosol model, which lets us not make assumptions regarding the aerosol mixing state. So what we like to do is we like to think of individual particles that we're tracking in this model as vectors of composition. So what we did is we can represent the volumes of the particles, and we can allow them to evolve fully due to coagulation, condensation, and other processes. And this is a very useful tool to generate many particle populations of a variety of conditions that we're going to want for this study. So how are we going to use PartMC to generate these diverse populations? So what we did is we took a bunch of variables that we considered important in terms of environmental variables, emission variables, whether or not we want sea salt or dust. And we constructed 1,000 scenarios using lead and hypercube sampling to probe this parameter space of varying 15 different variables. And as a result, we have 1,000 scenarios where these particles are all hopefully very different. So we're representing mixing states that are very externally mixed, very internally mixed, and so on. Hopefully, in the intermediate ranges. So our method of generating what we would consider what an instrument would see in terms of measurement samples. So what we do is we take a single scenario and we take snapshots of the particle populations at different times. And then we take those particles and call it our reference population, or chi-ref, which consists of 100,000 particles. And what we do here is we stochastically sample different sample sizes from this 100,000 particles. So in this study, we did 10, 100, 1,000, and 10,000, and we looked and calculated how chi varies for those different subsamples. And we repeat this 1,000 times to get adequate statistics. So how does this work in terms of a single particle population? So here I have a figure where on the x-axis I have sampled mixing state index, and on the far right would be 100%, where particles are fully internally mixed. Far left is where particles are externally mixed, and then the y-axis is frequency. So the chi reference point is the black dotted line around 48% or so, and this is the 1,000 samples of 10 particles each. And as we can see here, we get a whole range of mixing states that we're going to measure. ranging from about 20 to fully internally mixed. And the average is at about 70%. So if you only measured a small number of particles, you might think the mixing state is 70% if you repeated it multiple times. If you did it only once, you'd think it's somewhere between 20 and 100%, and you would have this huge amount of error. So if we increase the number of particles, we would expect the error to decrease, and which that's what the case is. When we sample 100 particles 1,000 times, the purple is the distribution that we get. And for 1,000 particles, better yet. So we're starting to really center our distribution around the chi reference point. And then at 10,000 particles, we're very, very close. So we did this for all 1,000 simulations for 24 different outputs for each of those. And as we can see here, this confirms the case of the single population that I just showed there. Is that in the case of 10 particles, you basically get this huge range of possibilities. No matter what you measure, you really don't know what the actual reference state is. And then, as expected, it increases in terms of accuracy as we go from 10 particles to 10,000 particles. And as we can see in the 10,000 case, it seems like the error is actually probably, or 1,000 case and 10,000 case, the error starts to become much more reasonable rather than having some huge range. So the question is, can we experimentally confirm these results using some actual measurements? And the answer is yes. So we took the Pittsburgh Metro data that I showed earlier as an example of spatially distributed mixing state. And we did that. We did 10, 100, and 1,000 particles from their samples particles, and then at different times of year that took measurements. And as we can see, we have good convergence. So 10 particles was really quite poor. And as we get to 100 particles, our answer is much better. So what we really want to know from this study is if you go out in the field and you measure a mixing state value, what is your uncertainty in terms of that measurement, right? So often with measurements, we want to be able to determine our uncertainty in our value. So what we want to do is actually look at confidence intervals. So here I have plotted the 95% confidence interval of 10 particles, a function of sampled mixing state. So if you measure a mixing state value of maybe 50%, you would expect your actual reference value to be maybe plus or minus 20%. And then here on the right here, I have the statistics. The difference or the range is 50, and actually the worst case scenario, which is actually at fully internally mixed, is 73%. So you could think that your mixture is actually fully internally mixed. It might actually be quite externally mixed. As we plot the confidence intervals for the rest of them, we can start to see that we really start to narrow in on these error ranges. And finally, when we get to 10,000 particles, the mean is a little over 10%, and the worst case scenario is basically plus or minus 10%, which we feel that you would have a very good idea if your particles were internally or externally mixed, or where in that range they were. You'd have some confidence. So just to sum up this talk, how many particles do we need to measure the aerosol mixing state? It really depends on what your error tolerance is, what you're capable of doing, and also it's a function of mixing state itself. In general, if we wanted to have around 10% plus or minus 10% error, we would need to sample on the order of 10,000 particles out of this 100,000 population. And then I just wanted to thank our funding sources, which is NSF, Department of Energy ASR program, the EPA, and all the computing was done on the Blue Waters system. PartMC is publicly available on GitHub, and the data that we used that consisted of all these scenarios is available at the link below. Thank you for your attention.